Very good afternoon to all of you. So welcome to this live session for the course Computational Fluid Dynamics for Incompressible Flows. So I'll just first clarify a few doubts from the discussion forum. Then I will take up the questions from you. So let me share the PPT. Okay, so there is a question in the assignment, the 9-point formula for discretizing this Laplace equation using a uniform step size as an order of accuracy. Okay, so this was asked. Actually, by mistake, it was set. So it involves this higher order discretization of this term using a 9-point formula that we have not discussed in the course. So you please skip this question. Okay, although the answer is 4, but when you discretize using 9-point, although it was not taught in the class, but you will find that order of accuracy will be 4. So I will discuss with the team and I will try to give full marks to all the students for this question. The other question, there was some confusion in the FTCS and BTCS. Okay, so there are questions like we are calling the backward time, still we are using the forward difference formula in del P by del T, values at n plus 1 and n, not n and n minus 1. Why is that? And another question is kindly show implicit FTCS and explicit FTCS discretization side by side so that concept would be more clear. So okay, so there are some confusions. There is no implicit FTCS. Okay, FTCS is forward time and central in space. That is itself an explicit scheme. Okay, and there is implicit scheme. Okay, so you can see. So BTCS is the implicit scheme. So there is confusion. So FTCS is always explicit scheme. So that means one unknown will be there, and BTCS is implicit scheme. More than one unknowns will be there. So now let me discretize this one-dimensional equation, one-dimensional unsteady heat conduction equation, which is your parabolic in nature. Sorry, del T by del T is equal to alpha del 2T by del X square. So now you can see that obviously this time derivative will use forward in time, and the central in space will use for the spatial derivative. So you can see that in general for FTCS, what we do, if we use this stencil, say let us say 1 point, this is I, this is I, this is I minus 1, and this is I plus 1. And now which way we are taking the time level? Okay, so delta T. Now we can say that it is n plus 1 and this is n. So n is current time level. Okay, n is current time level. Means n plus 1 is current time level where what is unknown. Okay, and n is the previous time level which is known. So using these stencil, we can use the forward time like T I n plus 1 minus T I n divided by delta T is equal to alpha. Now you use central difference for this time derivative, spatial derivative. So Ti plus 1 minus 2Ti plus Ti minus 1 divided by delta x square. Okay, so now as we are using forward time and central in space, so n plus 1 is unknown. Okay, this is unknown. And this is known from the previous time level. So as in forward time and central space, we will use that all are n. So we are forward in time. Okay, so that is the FTCS, and this is one explicit scheme because you can see that one unknown is there. Now if you see BTCS, okay, so now backward in time, here I got the confusion because you are telling why when it is backward in time, why you are not taking n minus 1. So I will explain it. Okay, so first let us discretize it, then we'll write the time level. So now let us say, so these are the two time levels and difference is delta t. Now question is that why we are not going in n minus 1? Because we are telling that we are interested to find in the current time level, which is your n plus 1, and n is the previous time level which already we know the values. Okay, so if we do so, then this is your n plus 1, all are unknown, and this is your time level n. Okay, and you can see that when we are using BTCS, so we are telling that this is your n plus 1 n, and all other also at n plus 1. So we are going backward in time, n plus 1 and n. So now you are telling that why you are not taking n and n minus 1. Then if you take n and n minus 1, then it should be unknown. Okay, and this should be known from the previous time level. Okay, so now if you say use the conventional way, whatever way we represent, n plus 1 always unknown. Okay, so that way BTCS is discretized this equation that Ti n plus 1 minus Ti n divided by delta t. Then all in the special derivative we are taking with the current time level which are unknown. Okay, so n plus 1 level, and these n plus 1 you can see that we have unknown at Ti plus 1 and Ti minus 1. Only known value is Ti. So this is your BTCS. So whatever way means you represent, say it is the convention we are using that n plus 1 is the current time level and n is the previous time level. So that way this BTCS we are using. Okay. So you should not tell that it is implicit FTCS. Okay. So this is a BTCS, but it is implicit because there are more than one unknowns. So there is a question. Okay, so one student didn't understand the solution. So for that we'll discretize this equation. So you can see that from this point there is a heat loss due to convection. Okay, so we'll use this convective boundary condition, and that is whatever heat is conducted at this point, this is convected from here. Okay, so that way you can write that Q double prime, that is the heat flux at this point. Okay, conducted is equal to Q double prime convective. So this is the heat flux. So you can see that you can write, so if this is the direction x, so obviously it will be minus k dt by dx is equal to, so it is due to Fourier's law of heat conduction, and from Newton's law of cooling you can write h t minus t infinity. So where del t dt by dx you are finding at 100 point, and this is the t 100. Okay, so now you discretize this equation. Now it is asked that using, you have to find the value t 100 using the values t 98 and t 99. So these 2 points you have to also use. So you have to use the discretization of this first derivative using 3 points. Okay, so you know that one scheme, one-sided discretization which gives second order accuracy, and that will be discretization like minus k 3t100 minus 4t99 at this point plus t98 divided by 2 delta x, and this is the second order accurate is equal to h t100 minus t infinity. Okay, so now if you put all the values, okay, delta x is given, okay, and all the values 600, 750, 300, heat transfer coefficient 250, watt per meter square Kelvin, thermal conductivity are given. So if you find the values, then it will come T100 as 350 degree centigrade. Okay, so now it is open for discussion. So if you have any questions, please one by one you raise your hand. Okay. Mr. Misra, you have any question?
Good afternoon, sir.
Good afternoon.
Sir, I do not understand the implications of characteristic lines. So you said that characteristic lines are the lines with the information.
Yes, I have gone through your questions. Okay, so it is actually means mistake. It is not across. It will be along. Okay, so it should be along. That you are talking about, right?
But doesn't mean that the solutions of the problem lies on that line only or surface?
No. There is a domain of dependence, right? So if it is you are talking mostly about the hyperbolic equations, right?
Yes.
So hyperbolic equation, because we have not touched here, only there's few discretization scheme we have discussed, because it is we have discussed mostly for incompressible fluid flow. So there will be a domain of dependence. Okay, so means there you will get the solutions, right? So I think you can refer. I think my student has given some reference of the book. Okay, you can please go through and clarify those doubts. Okay. Hello.
Hello.
Yes. So that you just clarify those doubts from the book, whatever he has suggested, or otherwise you just write to me. I will just give some books, okay? Because these are discussed mostly in the compressible flow, discretization, okay?
Okay, I'll see the book, and if I have doubt,
you please write to me, or I will take your email address from my student and I will reply, okay?
Okay, sir. Thank you.
Okay. Okay, so anyone? Ria, do you have any question? Uday Raj Singh? So you can unmute yourself and ask. So now which what is the module going on, Mr.?
That is week 9 is over.
So what is the topic going on now?
In week 9 it was MAC algorithm over.
MAC is over.
Yeah.
Okay, so in the explicit scheme already you have covered for the finite difference scheme, right? Using
Yes.
MAC algorithm.
Yes.
Okay, so I will encourage all of you to write some simple programs. I do not know whether for this discretization of elliptic equations and discretization of parabolic equations, like heat conduction equation, if you have you have written some simple code to solve. Say, let us say that you have a, let me see here, then. So simple some problem you just do. Say like you have, let us say, this is the solid domain. Okay. Now you solve elliptic equation. Let us say del 2t by del x square plus del 2t by del y square is equal to 0. Okay, and let us say that you have some temperature in these three walls. Okay, let us say you have 20, 20, 20, and this you have, let us say 100. So it is higher than the other three. So these solutions, because you can have the analytical solutions, there are some expressions. Okay, so that using that you can solve it, and after discretizing this equation also you can solve this problem. Okay, so now how to use the iterative techniques, right? Because when you will solve for Tij, so there will be neighbor points Ti minus 1j, Ti plus 1j, Tij plus 1, Tij minus 1, and you will start the solution with the guess value. Say, let us say in the domain everywhere you are starting with 20 or 0 value. Now with iteration, this will propagate and you will get the temperature profile like this. Okay, like this, because this is the isotherms same temperature. So like this you will get the temperature profile. So say only reading the books or watching the videos you will not learn CFD. You have to write some simple program on your own. So this is the simplest one. Then you can start with del t by del x. Del t by del t is equal to alpha del 2t by del x square plus del 2t by del y square. So now same problem you can solve using the unsteady problem, using the unsteady equation. Okay, although as t tends to infinity, this problem will become steady state. But say if you are starting from 0, let us say inside you have 0 or 20, let us say it is initial temperature is 10 and boundary condition 20 and it is 100, let us say degree centigrade. So now at t tends to infinity, it will become steady state. But how it is evolving with time, so that animations you can make, okay, solving this equation, and make sure that how you are using the iterations, because now it is a time derivatives are there. So with time you have to merge. Say this equation you are having the iterations only, but here you have to discretize either using FTCS or BTCS, and then you have to march in time and say march in time. So there will be a time loop, and also like you are solving this equation, you are going with the iteration. So inside there will be a iteration loop also. Okay, because in each time you have to converge. Okay, so using this iteration, because you are starting with some value 10, so now it should propagate it at all interior points, so it will be iteration. So now you have to give a check that when to stop of this iteration, and then you will go to the next time level n plus 1. So this is one simple problem. Then if you are a mechanical engineer, a famous problem is there, Quota Flow, right? So say this is flow between two parallel plates, but upper plate is moving with a velocity u. Okay, so you know that it is a shear driven flow, there is no pressure gradient, and at steady state there will be a velocity profile like this, because it is a u is equal to 0 here, u is equal to u. So what is the governing equation for this? Okay, so governing equation for this is parabolic, del u by del t, okay, is equal to nu del 2 u by del y square. If it is y, okay, so del 2 u by del y square. So now you can see that with time how the, say from if initial velocity is 0, then how the velocity is propagating, and with time how it is evolving. So you can see that it will with time it will have like this, and this way time is increasing. Okay, so these animations you should make. So these are some simple problems. Now when you are learning the Mach algorithm, at least two-dimensional some problem you can solve. It is a full Navier-Stokes equation you are solving, right, in Mach algorithm, and at last simple algorithm you will learn, and there you should write one full solver for Navier-Stokes equations. Okay, where you will solve the continuity equation, the momentum equation, and also you can solve the energy equation if you are interested. At least you solve the momentum equations. So two sets of momentum equation, at least two-dimensional, you can solve, so that you can solve some simple problem like in the MAC algorithm. I think I have discussed maybe lead-driven cavity problem. It is a very famous problem to start with. Okay, it is a very famous problem to start with when you are writing your own code to check it. Okay, so this is a problem like you have a enclosure. Okay, these three walls and are stationary, and the upper wall is moving with velocity u. Okay, so you can see it is also a shear driven flow. So due to this movement of the upper lead, there will be the velocity it will propagate at the interior domains, and flow will start moving like this. So it will depend on the Reynolds number, that how you are getting the vortices and in the corner vortices, and there is a way to check that along this vertical center line how the velocity is varying, and along this horizontal center line how the v velocity is varying. Okay, this is the u velocity along this vertical center line, and how the v velocity is varying. You can see that in this area, in these lines, it will be a negative v velocity, and this will be positive v velocity. So there is a well-known paper, Ghia et al., who solved this problem numerically. So this is the problem you should solve using MAC algorithm and simple algorithms. MAC algorithm, obviously, it is explicitly you can solve, and this way actually you will understand that what is happening inside. It is not so straightforward that you will write a solver or code, it will give the result. Okay, so there will be some mistake, or there will be some problem in the iteration, so you have to just fix the bugs, and then you need to get the correct result, because you have to get the correct results, right? Because you know that with some like this problem, so it is analytical solutions already available, right? For this I also told analytical solution is available, so you can compare your result with the analytical solution. Here also I told them numerical results are available, so you should compare your result with those published results, whether your results are matching or not. So this way you should write some code, and I think Mr. Mishra is more interested in compressible flows, so you should do some course on compressible, means like gas computational gas dynamics or some other course, so that you can also solve some compressible flow equations. So any other questions? Okay, I encourage you to write some, so you will get excited when you will get the results. Okay, and when you will plot, you will see, and the animations you will make, then you will see that when you are writing the code, how difficult it is, and if you are not getting the results, then you need patience to fix the bug. Okay, so that is most required. So I do not know, means from where, can you please introduce Mr. Mishra, from where you are and in which program you are studying?
I completed my BTech from IIT Kharagpur in 1984.
Okay, okay. So
age-wise, I am elder than you.
Yes, that 84 means long back. So where you are working now?
I have retired.
Oh, retired. Oh, so happy to see. But you work in some.
I was working National Tubro Limited.
Okay.
Then I left that job.
Okay.
I did my coaching in physics for IIT entrance examination.
Okay. Okay.
Was
good.
somewhat successful. Now I have retired from that. I am doing some research for a PhD.
Okay. Related to compressible flows?
Incompressible flow.
Incompressible flows. Oh, very good to know. And your means enthusiasm at this age. Very good to know, and nice meeting you. And Ria?
area is infrared suppression devices.
Okay, okay, okay. Thank you. Next, Ria. You can.
I'm able to understand, but I'm not very quick in answering and writing things.
Okay, okay. So, Ria, you can type if your microphone is not working. Okay, so hi. So from where means you are a BTech student or which program your work means there in which college? Oh, you are from BRC. Okay, so you are a scientist there or DGFS program or HBNI, you are doing some PhD? Mr. Uday Raj Singh, can you please? Okay. So BRC, so I have many friends there because the Unuprabha solver which we developed, you might be knowing then. So that was actually funded by BRNS, and many of the scientists from BRC were involved in developing this Unuprabha solver on unstructured grid. So other two, I do not know the name, something ECMEC. So it seems that from Assam Engineering College you are. Okay, so if there are no questions, so thank you very much. Okay, and we'll be in touch. And you please post your queries in the discussion forum. And Mr. Misra, I will just reply to you. Okay.
Thank you, sir.
Okay. Thank you. Thank you very much. Okay. Goodbye.
Bye, sir. Bye.